We've been concerned with eigenvectors and eigenvalues. Now remember, an eigenvector is a direction for which certain matrices will just end up stretching the vector, and the amount of stretch is given by this eigenvalue lambda. Now, the example that we've talked about in the past is a rotation by pi over 2. If we were to sit there and compute the characteristic polynomial, what we would find is that we'd get to this equation, lambda squared plus 1 equals 0. So we would have no solutions if lambda is a real number. And geometrically, this makes sense. So what the algebraic result is telling us is that there are no eigenvalues, so there'll be no eigenvectors. Geometrically, we're saying, look, if I take a vector, this matrix is going to have a geometric effect of just rotating. There is no direction for which any vector will get stretched. So if I give you this vector now, this matrix now, if I were to go ahead and calculate how a dynamical system with this matrix evolves, then there's some interesting behavior. So for example, if I were to take x naught to be 2 and 0, and I were just to calculate or iterate this dynamical system, what I would find is that I'd get a variety of different results. So if I were to plot them, what I would see would be some sort of pattern. I'd see that my x0 is approximately there, my x1 is here, so on and so forth. And what I would find is that there would be some sort of elliptical pattern for all of the iterates. I would really like to know if it's related to eigenvalues and eigenvectors. So in this matrix A, if I were to compute the determinant of A minus lambda I equals 0, in this particular case, I would be led to the quadratic equation lambda squared plus 1 is 0. So you could use the quadratic formula, and I would find that there would be no real solutions. And that would be the end of the road. I'd say, well, I don't have any eigenvalues, I don't have any eigenvectors, so now I'm done. I have to stop. So if we limit ourselves to lambda just being real and our eigenvectors just being real, we can't explain this behavior. And that's why we need our lambdas to be complex values, and we're also going to take our vectors to be complex entries. Last time in class, I talked about, look, if a matrix is n by n with real entries only, so no complex entries, and if it has an eigenvalue and an eigenvector pair, then this equation is true. AV equals lambda v. That equation has to be true. So if we are going to allow lambda to be complex, and if we're going to allow an eigenvector to also have complex entries, we're going to take this equation that we know is true, and we are going to then take the complex conjugate. Now, complex conjugation is just this operation where you take the imaginary part and you change its sign. It turns out there are some properties of complex conjugation. If you're ever to take the conjugate of a product, it's going to be the product of conjugates. If something is real valued, its complex conjugate is just itself. So the point of the story is this. In this case, the conjugate of the product is a product of conjugates. This is just going to be equal to A because A is real valued only. If you don't have an imaginary part, you are your own complex conjugate. And the point of the story here is that this equation is also true. And that means if A has an eigenpair of lambda and V, then you will also get the complex conjugate, and the complex conjugate of the vector are also an eigenpair. So in that example I showed you with the elliptical behavior, we had this matrix, and if we were to take this determinant and come up with the characteristic equation here, we would find that the lambdas would be 0.8 plus or minus 0.6 I. You can just use a quadratic formula to tackle that. And we would find then that in the case of, let's say, this eigenvalue, your eigenvector would be given by this result, or one of the eigenvectors, I should say. There's one. And if you were to solve for the other one, you would find that, just like we expect, the results would be different only because they'd be complex conjugates of each other. And that's important because that saves us a bit of work. All we need to do is find one of them to be able to understand what the other one has to be. To give us ourselves a geometric interpretation, the geometric interpretation requires real valued entries only. That's the way that I can actually see what the eigenvectors or values are doing. So our goal, when I start doing all of this technical stuff here, is to rewrite the results that we get in terms of the real and imaginary parts of lambda and v. Now, as an example of what I mean by that, in that previous situation, we got lambda was 0.8 minus 0.6 I. This right here would be the real part of the lambda. And in this case, the imaginary part of the lambda would be negative 0.6. That means whenever we've got a lambda, you can always write it as a plus bi, or if you feel like it, a minus bi. They always have to come in conjugate pairs for our situation. The eigenvector that we found was negative 2 or minus 4i in this particular case, and 5. So if I wanted to, I could write this as negative 2 and 5 plus I times negative 4 and 0. So right here, I could call this the real part of the vector v, and I could call this the imaginary part of the vector v. And if I feel like it, I could say, well, let's denote this as vector alpha and vector beta. And so that means whenever we have an eigenvector with complex values, we could write it as vector alpha plus I vector beta. So here's the technical result that we need. We are going to assume that our lambda has the form a minus bi. Now, why did I pick the minus here? Because it's going to make it easy to interpret my results geometrically. Our eigenvector, our eigenvalue like this in the form a minus bi, and that it has an eigenvector with a alpha vector is the real plus I beta is the real. And that's another advantage of using this notation. Okay, so we are going to consider what has to happen when you have this equation. On this side, you'd have a plus I beta. This is just regular old linearity. So that's pretty straightforward. On this side, you're going to have to do a little bit of algebra, a little bit of foiling. You'll get a alpha plus I a beta vector minus I b alpha. Now, in the next case, you're going to get a negative b beta and I times I. So those signs will cancel out and you'll get a b beta vector. So a alpha plus I a beta. So you have a real part and an imaginary part. We're going to group together the real parts and we're going to group together the imaginary parts. If we have a number that's complex, And each side will have then a real part and an imaginary part. If these two things really are equal, if this equation is true, that means the real parts have to be the same. And that means then that the imaginary parts have to be the same. And so what we can do is we can set them equal to each other. So we equate the real and the imaginary parts. We can do this as a matrix equation. On the left, I'll have the matrix that has the first column is A alpha, second one is A beta. Over on the other side, it's going to be a little bit spaced out here, but it's the same idea. This is a vector, and over there, we'll have negative B alpha plus A beta. This right here, this is the definition of a matrix times a matrix. This is what I called the theoretical definition of a matrix product. It would just be A times the first column of that vector, of that matrix, and B times that second column. So that means on this side over here, I have this as a product, A times P, where P is a matrix that holds the real part and the imaginary part. Now, the same sort of game is going to happen over here. I'm going to have the matrix alpha, beta. This stuff here is a matrix vector product. It's going to be A, B, and then the same sort of thing. Alpha, beta as a little matrix times negative B, A. This is the matrix P times AB, and then the second column would be the matrix P times negative BA. And so by definition again, this thing right here is P times some matrix C, where C, the first column of C, is this first thing right here, AB, and the second column is negative BA. Here's what we end up with. AP equals PC. And C ends up being a matrix that has these values from the eigenvalue, right? P is the matrix that has the real part of the eigenvector and the imaginary part of the eigenvector. We can take this equation and we can invert this matrix. And what we'll find is the following. C is not diagonal, and P does not have the eigenvectors. It just has the real and imaginary parts of them. A is not diagonalizable, is not equal to C, is not equivalent to C. It's this new phrase, similar.